So this talk has two goals, and in consequence, two parts. And you can guess both of them, because one is Fourier analysis, and the other one is a large library of formalized mathematics. Well, okay, more or less. So the first half of this talk is, well, first, I should probably explain what I'm going to talk about. Okay, so what I'm going to talk about is arithmetic progressions of length 3. That's that should be pretty easy. Like mathematically, it should be fine. So an arithmetic progression of length 3, I'm going to take it as a triple, a plus d, a plus 2d, for some a and d. And why do I see my, can I not write this? Okay, yeah. For a and d, two natural numbers. Actually, should be this. For two natural numbers or integers. And it's important that in this definition, I allow d to be 0, in which case I just have a 3 times. Okay, and if it's not 0, then I say my free AP is non-trivial. And my a set of natural numbers is going to be free AP3 if it does not contain a non-trivial free AP. Well, you can't cancel both knots. It's not the same as containing a trivial free AP. Okay, and now the main question that I'm going to try, well, I'm not actually going to answer it, because it's hard. But the main question behind this talk is, what's the maximum size of a free AP3 set in the first n integers? Okay, so let's have a think, and I have to teach you. Okay, and the other thing that I'm going to talk about here during this hour is Lean. And Lean is an interactive theorem prover, which is a dependent type theory. Not very relevant, that is dependent type theory for me. And to be fair, I just want to say what I'm using because I don't think Lean here is going to be particularly relevant. Mathlib, it's a library of mathematics, is going to be much more relevant. And a lot of people get confused. Lean and Mathlib are not made by the same people. You should not confuse them. Okay. And Mathlib is big. It has now 1.6 million lines of code, and well, it's hard to get the exact numbers of contributors because there was Lean 3 and Lean 4 and Mathlib 3, Mathlib 4, and we didn't quite manage to like match up the contributors on both sides. But we were above 400 in Mathlib 3, and we definitely have reached past 500 now, maybe even 600. Okay. So the first half of this talk is going to be about the actual mathematical problem, which I just explained with APs, and how I am formalizing it in Lean. I wish I could have said I could use this hour to claim that I have proved it formally in Lean, but this has actually not happened yet. So it will be more of a in progress review. And the other half is my personal workflow for contributing all the mathematics that I'm writing back to Mathlib, which is harder than one would hope. Yeah, and that's it. So let's go with the first half. First, I'll explain the history of the problem, like how it happened, mostly what year Erdös came up with it, and then I'll explain. I'll explain a short. I'll explain like a rough proof of the first important theorem that happened towards that question. And finally, I'll like list out. This is basically just humble bragging. I will be telling you about what I have done personally in my project, and I will explain the. You can try guessing what this stands for. Before we get to it. Okay, so question again. I remind you, we have a free AP3 set A between 1 and n, and we want to like bound its size, or maybe on here we're gonna try to first just build one set which doesn't have 3 units. And the first idea that we could possibly have is to build it incrementally. By like doing recursion on n. So here we're going to play a game, and this is why I really like to be in this room where there's blackboards. I am going to make you guess which numbers are. I'm going to, yes, I'm just going to move the laptop. Actually, you can move the laptop yourself. Okay. So for this part of the talk, yeah, the stick is. Okay. So for this part of the talk, it's important not to be British. Just people you cannot contribute. We're gonna start at 0. The first, so 0 is in our set. Okay. And now I'm going to ask you for each natural numbers in turn whether you want to take it in or not. Okay. So this is something for the audience in Cambridge. There's enough people to actually get to a sort of consensus. So should I include 1? Can I include 1? Yes. Okay. Can I include 2? No. 3? Yes. 4? Yes. 5? No. 6? No. Sorry, no. 7? No. 8? No. 9? Yes. 10? Okay, and a few more. 11? No. 12? No. Sorry, 12, yes, sorry. 13, yes. And then no. Up to 27. What's the pattern? So this is the set that we get. Okay, and I don't know if people can spot the pattern from this. I certainly couldn't because that's actually a bit shameful. The pattern is a bit more clear if instead of using base 10, I use base 3. And you immediately see that actually the numbers that we picked are exactly the ones which only use 0 and 1 in their base 3 expansion. It's not base 3. It is base 3. And that's great. And I think you can convince yourself that if I take A to be that set, then it would actually be 3A P3. That's an exercise for the viewer. And now we can try thinking about what the size of this set is when we like truncate it up to n, like you know how many numbers we get up to n. So we can just do it. It's actually not very hard because there's 2 up to in base 3. If I allow k digits, so if I go up to 3 to the k, but I restrict to digits 0 and 1, then out of the 3 to the k numbers, and we take 2 to the k of them. And 2 to the k is 3 to the k to some power, namely log 2 in base 3. Yeah, and that power is strictly less than 1. So you get something of the form n to the c for some c strictly less than 1. And oh, that's right. That's actually not Erdös, sorry. That should be Zcash. Zcash, when Erdös talking about this, said, "Oh, actually, it must be optimal for n equals 3 to the k. And if it's optimal for n equals 3 to the k, then you can actually get that it's there is some c prime which is going to be a bit bigger than c, for which it's actually this statement here, the n to the c is actually true not just for n power 3, but for like all n's. So you cannot just interpolate between powers of 3, and that doesn't use you very much. Okay, so that was the conjecture of Zcash. So yeah, Erdös didn't actually conject that, and we can start putting things on the scale. So we start with this. So on the very far right, we have the trivial upper bound of n. I mean, you know, there's at most n numbers to pick. So yeah. And on the lower bound, we have this 3D construction, which I just explained, where that c is log 2, 3, log 3 to whatever. And I'm going to use colors to distinguish the lower and upper bounds. And on this scale, Zcash conjecture is here. And you can guess by the amount of blank space that I have left that this is not very true. Sadly, after his conjecture in 1936, the original paper by Erdös and Foran actually, Berendt came up with a construction which is much, much bigger. And by much, much bigger, I mean like that much. New orders of magnitude. So Berne's construction is actually very, very beautiful, and I would really like to explain it. I don't really have time. Maybe there's time at the end of the talk, I expect. And Berne's construction is like almost, it's almost linear. Like the first order term is n, and the lower order term is this square is the e to the square root of log n. If you think e to the log n would be n, but e to the square root of log n grows much, much more slowly. And this low amount is actually still the best now to this day up to second order terms. Actually, you can replace this e by like 2 square root of 2 to the 2 square root of 2, something like that. We don't really care. And most of the progress on this problem has come from the upper bound instead. So the first major result was Roth's theorem in 1950. Maybe about the date wrong, not exactly sure. And Roth proved that it was sublinear, and so he got it to be like n over log n, which is actually pretty good. Like it's effective. And this proof has sparked a lot of interest in the problem because it seemed very intractable before, and after that it became manageable. And but log n still grows very, very slowly, and it's like miles away from e to the square root of log n, as pointed out by that space. And the main reason we're interested in this, the main reason we are interested in quantitative bounds on this problem is that we would like to be able to prove it when A is we would like to be able to prove that A, the set of primes, contains arithmetic progressions of length 3. So of course, okay, set of the primes to contain arithmetic progression of length 3 is not very hard, but like, the question is kind of like if you truncate it, yeah, like, you remove the first 2 primes, and then you kind of like look at what's left, and then it's not very clear already that has an arithmetic progression of length 3 or not. If you know, there's the Green-Tau theorem, which actually states that, but the Green-Tau theorem uses a lot of number theoretic machinery, which is specific to the prime numbers. Typically, if I take the prime numbers, but I move like half of them, or if I take the prime numbers and I move them by like plus or minus 1, then their proof just completely breaks. We would like to have a way of proving that arithmetic progressions of length 3 exist in the primes without using anything about the primes but their density. And importantly, their density, I'm going to rewrite it. Actually, I can't really write it anywhere so that people online can see it. Maybe here. If you see it, I think you see it. The density of the primes up to n is n over log n. So this is basically the barrier that we need to break. And and this finally happened in 2021 with this n to the log n to the some constant bigger than 1. And this was already a breakthrough. This was huge. And the proof was not so hard, but still, it was actually quite complicated for what it was. But of course, it had to not use anything about the point. And up to like 2 years ago, that was the best we had, and that was it was like still a huge gap between this log n and e to the square root of log n. And that was finally bridged by 2 computer scientists, Kelly and Mecca, who finally proved a bound of the same shape as Berne's. So they proved exactly the same thing. They said that this log n is not to the power of 1/2, but to the power of 1/12. So it's really, really close. And okay, so now I can finally tell you where we are at in Lean on this scale. So on one hand, Berne's construction is in Mathlib. It's been since 2022. Thanks to Babik, who people know here, and we put that in Mathlib. And Telemeka, this is the big project that I'm going to tell you about. This is APA. This is the concept of APA. And Telemeka is pretty interesting in that its proof is basically the same as the proof of Roth's theorem from 1953. So actually, I'm not going to explain this proof. I'm going to explain that one instead. So this is what's coming up next. We're going to explain Ross theorem. Okay, and let's go. So this is I definitely got the date wrong. That's 19 questions. So let me state Ross theorem properly. So if you have some set A in the first n integers, which is 3 then the size of A is at most n over log n. And here, every statement that I'm going to put in this talk will be asymptotic, because typically if I take n equals 1, this is negative, so it makes no sense. So everything is gonna be for n big. So the first step is assume that you have a set which is bigger than that, and look at its density. So its density here being, what amount of 1 to n does it take? And this is going to be also, I forgot the absolute values. And by assumption, its density is greater than log n inverse. So I'm actually not going to tell you how I find, how does that log n come up? But I will get you to a point where you can believe me that doing the quantitative calculations, you will get that, or something similar. Okay. And the very important idea here is that we have a dichotomy. Our sets are like our set A will fall in either of two categories. Either it is structured, or it behaves like a random set. And now I have to tell you what I mean by structured and random set. I hope you can see it. Yeah. So by structured, I mean that there exists a long arithmetic progression, so not 3AP, but much longer, which once intersected with A gives me like a set A prime, which has a big density on my arithmetic progression. And the other case is when such arithmetic progression doesn't exist. And if such arithmetic progression doesn't exist, you should expect that A is roughly like equidistributed. There's no, it doesn't like stick, like its density doesn't stick out in any on any arithmetic progression. So somehow if you like try to prove progression and you get to just what you would expect from a random set, and it should actually be like basically a random set. And this will quantitatively be done using Fourier analysis. And we're gonna say that A contains about as many arithmetic progressions of length 3 as a random set of the sets of the same size. Okay, so let me give you some quantitative results here to explain, and make the statements in the previous slide a bit more precise. So using Fourier analysis, which at least 1 to 2 persons in the room will have seen in lectures, for all alpha between 0 and 1, so my alpha is actually P for A, there exists some epsilon greater than 0, such that for all n and A of density alpha, we have either an arithmetic progression of length P, which I'm going to call P, of length at least square root of n, such that the density of A, sorry, that should be P, sorry, density of A over P, so it should be A intersection P over P, is at least alpha plus epsilon. And this is good, because this is more than what I had before, which was alpha. Or the other option is that A has roughly the same number of progressions as a random set of density alpha. And now you can make the calculation. So let me do that quickly. An arithmetic progression looks like this. I have A plus D, A plus 2D, and there is n choices for A, roughly n choices for D. I mean, not Y, because I'm going to get out of n, but I don't really care about that. That's just a factor of 2 or 3. 4. And A plus 2D. And each of those is going to be in my random set of density alpha with probability alpha. I mean, they are not quite independent, because once I've taken the point out of my set of density alpha, then this density is not quite alpha, the density of the rest is not quite alpha, but it's negligible. So this is with probability alpha in my set, my random set. And then because I had n choices here for A and n choices here for D, the other one is fixed, given those, I get exactly alpha cubed times n squared half-width progressions in expectation in my random set. And now, assuming that my n is not too small, this is greater than alpha n, which is exactly the number of trivial arithmetic progressions in A. So if the number of arithmetic progressions in A is strictly more than the number of trivial arithmetic progressions in A, that means that there is some free APC in A, which is actually non-trivial, and then I have one. This is what I wanted to do. Okay, this is the gist of it, and now let's put this randomness structure dichotomy into a recursion, which I'm going to call the density increment strategy. So in the first case, the quasi-random case, we are done assuming that n is not too small. In the second case, we replace our original integers from 1 to n by this long arithmetic progression that we found. We intersect A with it, and the density goes from alpha to alpha plus epsilon, or maybe at least that. I don't remember because it's more. And now, because the density is bounded above by 1, that's how density works. This second case here, the structured case, will only happen at most, 1 over epsilon many times. So now, after 1 over epsilon many times, my original n has become like square root of square root of square root. Sorry. No. Okay. My original n has turned into a square root of square root of square root of square root epsilon inverse many times. And so I need to check at the end for the quasi-random case to actually work. It's that n to the minus 2 to the epsilon inverse is greater than alpha to the minus 2. Okay, and actually I've lied a bit because epsilon here depends on alpha, but actually depends on alpha in a good way in the sense that when alpha increases, my epsilon doesn't get worse. So it's fine. I can keep the same epsilon for all alphas. And now, if I can show that I can pick my epsilon to be like quantitatively good in terms of alpha, then this becomes some inequality in terms of alpha and n, and then I can solve that. I can solve that in terms of n to get an upper bound on alpha, and that upper bound would be log n inverse. Okay. And yeah, so I've explained you Ross proof, and I've basically also explained you the Kelly-Mecca proof. The most important difference, in my opinion, is that in the Kelly-Mecca proof, we don't restrict to a long arithmetic progression. We do something more complicated. We talk about something called the ball set. So we're not explaining what a ball set is, but roughly speaking, it is a subgroup which is not quite closed. It's kind of closed under addition of small elements. So it's like, if I pick every second integer in z over 2 and z, then I pick like 0, 2, blah, blah, blah. And I look back and I will I won't pick 1, 3, etc. But if I were to do the same thing in z over 2 n plus 1 z, which is almost the same thing, but not quite, I'll go 0, 2, 4, blah, blah, blah. Then I look back and I'll go pick 1, 3, 5, and so my subgroup will actually be everything. And this is bad because somehow I want z over 2n z and z over 2n plus 1z to behave the same. So a ball set kind of prevents me from adding too many times and eventually picking everything. And yeah, that's roughly the idea. And so if you do a ball set, then you will be able to get to that length, which if you remember was square root of n, to something much smaller. Okay, and yeah, and also we'll work a bit harder on the randomness structure dichotomy. I mean, especially because we're now restricting to something more complicated, which doesn't look like what we started with, to get better bounds. And finally, we will actually not start with the set A. We'll start with the set A like slightly processed before we do this recursion with the density increment. This is also one of the few differences. This doesn't have a lot of incidence on the rest of the presentation, so if you don't understand it, this is fine. Okay. And now, what does this actually give me in Lean? for this randomly structured dichotomy, I need Fourier analysis. I need Fourier analysis in a way which is usable for me, and because everything here inside is finite. I mean, I have the integers from 1 to n. And that, okay, that's not a finite group, but I can make it close to a finite group, so it's fine. So all my Fourier analysis will actually be discrete and finite and compact. And so a bunch of like measurability, integrability, continuity, all of those things I don't care about. They should not bother me. So it's kind of important to make something that's suitable for my specific use case. And then to do those calculations, because I've explained you this n to the -2 to the epsilon inverse, that's nothing. This is very easy calculation compared to what we're gonna get in the actual code. So we need like a good set of tools to do the calculations. And finally, because I've explained, I need Bohr sets, so I need to like develop the theory of Bohr sets, which is mostly due to Borger. This is actually not done yet, so forget about this. I won't explain it. Yep. And now let me show you. Sorry. Sorry. What? Yep. And this was so you can find all the code on my repository, which is my first name dot my last name. Sorry, my first name not my last name .github.io/linabap. And now you can finally have the answer for what ABAP stands for. It stands for arithmetic progressions. Okay, you better guess that. And almost periodicity is one of the important results that make that possible. I won't explain what it is. Except maybe people in the business will want to know, but after. Okay, so the discrete Fourier analysis starts. How do I do it? I need a version of the LP norm, which hopefully everyone here knows what it is. So the LP norm is like the integral of the LP norm function is the integral of the p power of its values, all to the power of 1 over p. And in Mathlib right now, it is only a version which takes in infinite values, possibly. But because I have everything is finite inside and all my values are finite, I shouldn't have to care about the infinite values. So yes, I need some version of the LP norm, which is, so the Mathlib LP norm is E LP norm, which takes in only finite values. So to decrypt you a bit what this is, hopefully you understand that r greater than or equal to 0 infinity is well, like the non-negative rational real numbers extended with infinity. And this is the same thing, but without infinity. Here, my G is some finite Abelian group, and E is some non-space. And my setup actually allows for an arbitrary weighting by a measure on my finite Abelian group G. Okay. And then the P in LP norm appears as an exponent. Okay. And from this very general definition, I get two specialized definitions for the discrete LP norm, which is the one where everything has weight 1, and the compact LP norm, where everything has weight 1 over the size of the group. It's actually important to have both, because when you do Fourier analysis, you compare the physical side with the Fourier side. And if you know a bit about Fourier analysis, you have seen things like Parseval and Tascherer. And those statements work much more nicely if you put different normalizations on the physical side and Fourier side. So in particular here, I have decided, and this is the usual convention as for matrix, that my original group G here will be equipped with the compact LP norm, and its dual group will be equipped with the discrete LP norm. I will explain what the dual group is. Dual group, for anyone who doesn't know. So I write it as G hat, and it's defined as the function from G to C, which respect multiplications. G to C, so to union complex numbers. And importantly, it's I can do Fourier analysis on this in a nice way. And okay, so now I have the epinors. I also need the inner product, and the inner product here is looking slightly different, but essentially the same. I have some weight W from G to the real numbers. This would have been a measure. It is not for simplicity, simply because I'm putting in values. I don't take the integral. And then I have the two functions which I'm taking the inner product of, which are going to be in this generality, they're going to be dependent functions from for each element of the group. I have an element of some known space, and the value is going to be in some in either R or C, which I'm denoting K here, and this is going to be the sum of the inner product of each value. So think like just the product with conjugate on F, multiplied by the weight. And similarly to this is the inner product version of NN and Pinon, and then I recover the discrete and compact inner products by putting in different values of W. And then I give notation to everything. And okay, so my Pinon didn't quite accept my fancy Unicode notation, so it has been downgraded to with symbols, and also spaces here, but don't forget about that. This is much nicer on the report, you check it. So typically this is Erdös inequality, which tells me that if I have two conjugate exponents P and Q, and functions, arbitrary functions, F and G, which here are put to R, but they're closer to C, then their inner product is at most the LP norm of the first one times the LQ norm of the second one. So all of this could be stated in Mathlib right now, but without all of this notation, it becomes a mumbo jumbo of integrals, and I don't find it particularly readable. And you also have to turn because F and G live in the same space. You can't possibly put both the LP and LQ norm on that space. So you kind of need to like transfer F and G to different spaces and then take their norms there. And it's kind of painful, and you have to deal with that all along. Anyway, it is much nicer to have some nice notation for it and some dedicated function for it as well. And this is one of the key points of my formalization, I believe. Okay, then I need convolutions. So convolutions, you should think are kind of representing how you. I mean, you all know convolutions because this is how we multiply numbers. And so how we multiply. The way you multiply numbers is, you have like 1, 10, hundreds, and then to get the hundreds position, you multiply the 1 and hundreds, and then the tens and the tens, and then the hundreds and the 1, and you add them all together. And this is exactly what's happening here. You should think you have two functions F and G from still the same function in the group. You real complex numbers. And for every value of my group A, I'm going to like sum over the pairs which add up to that A, of pairs A, B, and C, of F of B times G of C. And yeah, this is very important because typically my office progressions can be encoded using convolutions. Again, not necessarily to explain it here at this point, but if you have questions. And something else I'm going to need is the difference convolution, which is very similar to the convolution, except that this plus here becomes a minus, and I add a conjugate on the right. So this is the conjugate for this is the convolution of F with like the conjugation negation of G, which kind of takes the conjugate and also like puts in a minus inside the G. So it's post-composition with conjugation and pre-composition with negation. And I will also need to be able to iterate convolutions. And so I defined this iterconv, which is similar to like natural powers in any group. And I give you an example theorem, which I can prove with all this isolation. So this says that the difference convolution here distributes over, the iterative convolution distributes over the difference convolution. So it's a version of n times a minus b is n times a n times a minus n times b. Okay. And my point here is just to show what the notation looks like. I don't really care about that specific statement. Okay, and finally, what you've been here for, this is the Fourier transform. And so ADCAR GC here is the dual group to G. And so the discrete Fourier transform, it's in a function from the group to the complex numbers and spits out a function from the dual group to the complex numbers. And it is quite literally defined as the inner product with X. So this is the usual vector. And here this is going to be the discrete inner product, which is why it's called the discrete Fourier transform. In practice, in my application, I will use the compact Fourier transform instead. So I add a little n here, which is this notation, which is just the same, but like divided by 6. And so the partial identity tells you that the inner product of the discrete Fourier transform of f and g, of the discrete Fourier transforms of f and g, is the same as the inner product of inner product of f and g. So this is nicely done with this notation. And then I can get a Fourier inversion, which is which I've actually sorry. And for the Fourier inversion is a way to recover the original function f from its discrete Fourier transform alone. And this looks very much like the definition of the discrete Fourier transform itself, except that you have you replace the sum by an expectation, and then you also are missing some conjugating sum. And the very important theorem, and this is badly translated in my Vimo because my Vimo didn't accept \ast as a symbol, so you have to think that this is a convolution, this f convolution with g, and this is multiplication. Suddenly they look the same. So I'm sorry about that. And the very important thing about discrete Fourier transform is that it kind of turns convolution into multiplication. And this is very useful. Okay, enough for discrete Fourier analysis. And now let's go on to the calculation tools. So the first one, which I really like, is positivity. So positivity is a tactic, so namely a proof generating program which knows how to prove things of the form A greater than or equal to 0, A strictly greater than 0, or A not equal to 0. And this was originally written by Heather Magrath, which I find very much. And my contributions on here have been multiple and spread across 2 years. So the first one was that this A not equal to 0 was actually originally not in the scope of positivity. It only knew how to do the first two. This turns out to be important because sometimes you can prove in one way that A is not equal to 0, another way that A is greater than or equal to 0, and like if you put that together, you get A is greater than 0. And then the way positivity works is that it looks at the structure of my A and puts a proof together. So maybe I should actually do an example at this point. It
does different things from omega Lewis.
It is very different. It is very different.
Omega is only introduced as well.
What?
Omega is only introduced.
Integers and natural numbers, yes.
Yeah.
So let's say I want to prove that 0 is less than or equal to a squared times the norm of x. Then positivity will see that, and it will say, oh, it's enough to show that a squared is non-negative, and also that x is non-negative. And then it sees that this is always negative because the norm, so that's norm. And then it looks at the exponent and sees, oh, it's even, so this is also done. And then it kind of puts the proofs back together to prove this.
So if you move the board down, so it's kind of like sitting in the white area.
Yeah, that was for the people in the.
Oh, right.
Yeah, but they have seen now. So. Okay, so you see, for every single possible sub-expression that could appear in a positivity goal like this, we need what we call a positivity extension, which is like an extra piece of code which puts the proofs together. So they're usually not so hard to write, but still, like, somebody has to do them. So a lot of my contribution on positivity was to write a bunch of this. So typically, if I have a set A which is non-empty, then I can prove that its size is positive. Sounds a bit boring, but it was actually not so easy to do. And importantly, I can also prove that the sum of a non-negative function is non-negative. And if I combine them with the previous point, then I can also prove that the sum of a positive function is positive if the set is non-empty. Yeah, so that's useful. Okay, and a bunch of other things, which are too numerous to count and not useful to mention. Okay, and positivity is particularly useful when combined with another tactic, which is also structural. It's called decong for generalized congruence. And decong proves goals by monolithicity. It looks at the expression on one side, looks at the expression on the other side, and then kind of sees how much the structure looks at the structure that matches up and tries to show that like looks up its list of theorems, and if one of them says that this structure is monotone in its arguments, and it lists that as goals. So typically, if I have I should have probably moved the times here. If I want to prove that A is equal to A prime B prime, then calling decong on that will automatically turn this into 4 goals, namely A less than or equal to B, A prime less than or equal to B prime, and then 2 non-negativity assumptions. Except that if positivity manages to close these goals, then they don't appear. So that happens more often than not, and it's particularly useful. And again, thanks to Hazard for having written this. Okay, and here I don't have any specific thing that I've done, but there's plenty. So I have taught decong about many such functions such as mul, which made it more useful generally, and in particular for me because I was looking to use it. Okay, and then there's a lot of other tactics which I use a lot of times. So the first one is norm, which simplifies numerical expressions. So it's kind of a very small computer algebra systems. It knows how to prove things like 0.69 minus 2 is minus 1.31 and stuff like that. And it also knows how to prove inequalities. There is some limitations to that, which I will come to later. And then there's 2 linear arithmetic solvers, and then linearif and omega, which people were mentioning. So linearif works for things like real numbers, and omega is a slightly stronger version, which only works for integers and natural numbers. And omega is stronger because you have to think there's no natural number between 0 and 1, etc. So you kind of every time you have a strict inequality, you can turn it into a much better a weak inequality, and that means that you can prove more things. Yeah, omega is particularly useful when you have things which are kind of fiddly to prove about natural numbers. It does them so long as they are linear. Sadly, there's still a gap here. We would like to have things which prove a bit more than just linear, but whatever. Okay, and last one is ring, which simplifies ring expressions. So the typical way I would use that is I have like a long series of a long product which I want to reorganize in one way, so I can then apply decong on it on a specific factor of it. And it's really annoying to do it by a series of swapping those 2 terms here and then doing associativity so that this becomes that. And ring kind of just all of this for you. And I didn't find Anna, but that was Anna Bannon who wrote this. Okay, so now let me give you and the final thing, calc, which is a very useful tool to structural calculations. And now I'm going to show you a big example coming from the very last proof in APAP. So I don't really expect you to understand what's going on here, but I'm going to pick out a few examples to demonstrate the use of those tactics. So you see, first is there's a lot of GCOM. So here, typically, you can see on that line, there's log 2 over 2 less than 2 than some number over 2. And the way GCOM is going to work here is it sees that this over 2 is the same as this over 2. So it will leave me to prove that log 2 is less than or equal to this number. And this turns out to already be in my local context. So GCOM just closes that off. And that happens a bunch of times. Typically here, it goes from this line to that line. I have the same 2 to the 156. Then I have this times LA to the 8. And this is 1 plus 0 to the 8. So it's going to turn this into 1 plus 0 is then equal to LA. And actually, LA you don't see here, but this is just notation for 1 plus log of A. So this will actually just become 0 less than or equal to log of A. And then positivity will actually positivity won't do it. It will, but I have stated somewhere that then 0 is equal to log of A, so GCOM will close that. And then here I have this 1 plus log of A, which just turns out to be LA, so GCOM also deals with that. And so the usual way I will prove something using all those tactics is I first write. I write my first left-hand side, and I apply some inequality, which here I already have from the context. And then I rearrange that big expression to something which I can use GCOM from. So in that case, you see there's like this factor of 4 over log q, which I'm putting on the side. And then the rest I put together. And then I call, then I turn that big expression into something different. And the way the parentheses are right now is that this 256 and 1 plus 0 to the 8 are together, and this 1 plus log A second is going to correspond to that thing. So GCOM on this is going to leave me with the goal that 4 over log q is less than or equal to that big thing, and log 2 over 2 plus log A is going to be less than or equal to 1 plus log A. Actually, it's not even going to do that because the log 2 over 2 is the only thing that differs in the expression. So I'll be left with log 2 over 2 less than or equal to 1. And this is what this calc thing here is called. Okay, and now we can talk about the limitations. So I've written them on one side, but now I'm noticing I might as well prove them. Show them here. The third one that might be obvious already is that why do I need to write explicitly that log 2 is less than or equal to this horrible thing? You know, like num should, if it's really a computer algebra system, should like tell me directly that log 2 over 2 is less than or equal to 1. Like, you know, that should come for free. Basically. I mean, I could have proved it from the fact that log of x is equal to x, but like, you know, I want a general solution, not one which works because I have like the good numbers. So right now I'm kind of I have to do another catalog to prove something which is in 3 lines, which would really be just one. And the other one is that you see, like this third line of my calc proof is a bit weird, right? Why do I have 1 plus 0 to the 8? That's just 1. The reason I have this is because I want to call GCOM with a goal that looks like this, but with non-stupid numbers put in. Namely, the 0 is going to be turned into log A somewhere there. And so you would like somehow to be able to skip those intelligent statements which are a bit stupid to read. I don't actually have a good solution for you. Oh, question. Yeah.
Why are 2 numbers for log 2 different? It's 0.8 and 0.3.
Oh, I'm guessing there are.
There's a times LA here.
If you go on, there's times with 0.8 and the other times with 0.3.
I'm guessing they're upper and lower bound.
Yeah.
Sorry,
Well, this
Look at
the 2 massive
0.693
numbers. The last digit of the 2 massive numbers.
One ends in 03, one ends in.
Oh yeah. One is a lower bound and one's an upper bound there.
Okay.
Because I'm dividing, so I need
Oh,
I need the other side.
nice.
Makes sense.
Yeah.
Wait, so can I just, where did you get those bounds from? Like you said, they're already in the context. Was there another tactic?
They were in the library done by Panic 3 years ago.
Oh.
We still don't have, like, you know, it should be part of normal, right? We shouldn't have to state them already.
Okay, so GCOM just has like a bunch of bounds that it kind of like looks up sometimes.
No, I literally just put it in the context of that. Donald doesn't even know about this.
Yeah.
Which is why, like, you know, it's
Yeah.
kind of antiquated as a system. You have to put your bounds by hand by doing some kind of like tidal approximation, and then you can use them in Donald using this weird G-conv and then blah, blah, blah. It deserves a rewrite at some point. And yes, and then at the end, you know, once I'm done with my G-conv applications, I can get back with a ring. Okay. And now let me do the same thing with a series of bullet points where you don't see the relevant codes anymore. So I told you this weird thing is weird. Yeah, the other thing I didn't mention is that those tactics are actually quite expensive. They've been made much faster from Lean 3 to Lean 4, but this is still very noticeable that they are like not very optimized. In particular, this file, which I picked this proof from, is only contains lemmas. Maybe I shouldn't call them lemmas; they are like theorems, but proposition, 3 propositions, and this still takes a minute to build. In particular, every time I modify one of those lemmas, like, you know, every single keystroke is going to be 20 minutes of my life lost. 20 seconds, not 20 minutes, which is too much. I would like to lose less of my time.
Which tactics take all this time?
G-conv is fast.
Okay.
Positive is fast.
Yeah.
Ring is not that fast. Normal is also fast.
Are there
Linear
proof
is also...
extraction tools for them?
What?
Are there proof extraction tools for them? Like a big question.
No.
Is that possible?
Yes, but I don't think you want to, because they would take up too much space, and they would like you see my. If I were to expand the proofs here, then like this would not fit on one slide anymore. It would be like 2 or 3 times as long, and I don't think this is particularly. This is not what you want, right? You don't want to write. Yes, exactly. Yeah, thanks, Eric. I don't know why you put it on Zcon, but good choice. Actually, no, bad choice, because Zcon is actually for the output to find proof. Yeah, and but all of this to say anyway, like this combo is very, very, very powerful, and we kind of just need to make it like, you know, not force you to have those intermediate steps which are like a bit weird, and also make it faster. Okay. So I think I have reached this part of the calculation tool, and now I can summarize everything. Right now, my library AppApp is the one place which lets you do discrete Fourier analysis in Mathlib using Mathlib. This really should change by putting it in Mathlib. And this is you see the transition with the second half of the talk now. The issue with this is Mathlib likes generality, and my thing is very concrete. So so we have we have like an issue that everything that I contributed, like the positive extensions, the G-conv lemmas, all of this were incorporated like orders of magnitude faster than the totally new contributions, like the discrete Fourier transform. The discrete Fourier transform actually is not Mathlib yet. This is like, and I've been trying to put it in Mathlib for like a year and a half now. The reason is, like, you know, there's like maybe 15 lemmas that 15 pull requests that lead up to it, and every pull request takes like, you know, it takes me like 1 day to write. Then it has to vote for like 2 or 3 weeks before I can ping someone, and then another person, and like, you know, after a month and a half, someone finally reviews it and says, okay, no, I'm done. And that's an issue, because then every single pull request in that pile of in that chain of leading to the discrete Fourier transform takes 1 month and a half to be merged. Okay, but now I think I should explain the second. So this is going to be much less structured, not least because I had personal life troubles yesterday to write those slides. But also because simply it's going to be much more nicely shown with actual websites than slides. So the first part, I will explain what Mathlib, how Mathlib is structured. How am I doing with time? Good, perfect. we're half. Amazing. This is, I wasn't planning on being half.
But you can sort of get it straight with it. So.
Oh, yeah. Oh, wait, is it on time?
No.
Oh, it is on time. Okay, fine.
Yeah.
Oh shit. Okay, then I've been much more than I expected. Sorry, I thought this was hard, but this is 6 p.m. Then, like, you know, how you write code with upstream in time, and then finally how you contribute to Mathlib with that. And I guess the structure of Mathlib I will skip pretty quickly, but basically there's like 3 categories of people, and each one include the next one. The first one is the maintainers, which are like, you know, the people who actually agree on what goes in Mathlib and what doesn't. And then so they are like responsible for everything. Then the reviewers are the people who like mostly are the people looking at the content and making sure it actually is good, etc. And once they're done with this and happy with it, they tell the maintainers, and the maintainer will have a fine look and usually just fine. And then everyone else are the people writing new content. And I should mention, if people are writing new content and are not reviewing, you're allowed to review. This is fine. I don't know if anybody is not doing that, but you can review. It's fine. You just won't get direct access to the maintainers. Okay, and Mathlib is very, yes, exactly, encouraged. And like actually, Mathlib is very active. So if you know a bit about GitHub, we get roughly 40 or 50 pull requests merged per day. Which then amount to roughly 50K lines of new code every month. And currently we have more than 1,000 pull requests open. All of this to say that it's actually very hard to get something like there's just like much more to review than there is reviewing capacity. So how do you make your code stand out? Well, there's 2 parts, right? There's the part where you first write it. Oh, and this is the not necessary. So I need to show my where you first write it. So I'm going to give you an example here. Which stands from FLT, and it's 263. No, it's not 263. It's 223. Sorry. Okay, so this is something which I've written with Javier Lopez Contreras from Imperial, and we're proving some things about, you know, like how measures. If you don't know what they are, they're basically just translation invariant measures on locally compact Abelian groups. And we were proving something which was located in this file. Yeah, see this one. And, you know, we started proving something about harm measures, but in doing so, we needed to talk about, like, you know, product of sets of real numbers as a set of complex numbers, which is like this funny time C. I don't know, I'll just zoom in because you're not seeing anything. Okay. Oh, too much. No, actually, that's fine. This thing, yeah. And you know, we typically want that if both sets are compact and the product as complex numbers is compact, and that didn't exist. So then one solution would have been to write this one lemma, you know, like above here on line 17, and just like be done for the day. But instead, what I told Javier is you should create a new file, you know, which corresponds to the one to the place where it should belong in Mathlib. And so this is the file. This is the relevant lemma. Is compact.reprod_m, and you see its proof is the simplest application of all the things that already do this. And it's proving exactly that the product of real numbers of sets of reals as a set of complex numbers is compact if both sets are compact. And how do I know which file to put it? Well, I cannot just write the proof once. Then I use a tool called min imports. I've run out of jokes. I'll explain it later. And min imports tell me that actually the only imports I need are mathlib.ns.complex.basic. In particular, that means that I can just stick that lemma at the end of that file, and that everything will compile in Mathlib once I'm done. So what do? I create a file called flt.mathlib.ns.complex.basic, which is like what you see about here. And I stick my lemma in there. This is very important. I just cannot emphasize how important this is. But setting your project to do this instead of like putting random lemmas in random places makes it much more much easier for them to actually upstream it to Mathlib. And okay, so you see here we've done that with a bunch of things. So typically here, like, you know, every single file which is like in this Mathlib folder is one thing that should be fixed in Mathlib, or one lemma that should be added to Mathlib in one way or another. And like, you know, sometimes you just leave it to do, you don't even like write the lemma. And here there's a bunch, and all of this, you know, every time you in the file flt.mathlib.x, you should only import mathlib.x, or maybe flt.mathlib.y, where mathlib.x imports y, and you put your lemmas there. And then how do you actually like, you know, get that to work with your workflow? Well, you use a website like this, which was just made. Well, okay, I had a version of this like ages ago, which looked like that. Actually, I can just show it to you. And the very important thing is this list here. This is the list of files. So not from the FLT project, but from my other project, Lean, which do not depend on any other Lean file. In particular, I can just PR them, which don't depend on any Lean file, and also don't contain any sorry, which for people not doing Lean, so I don't know, I guess you do Lean for here, is like, you know, means it's not finished. So all of these are ready to be upstreamed. So I can, when I open PRs, what I do is I just like sit in front of this list and I'm like, okay, well, I click on this one, I copy paste this code into Mathlib in one place, open for request, bam, done. Next one, click, bam, done, etc. And it's actually really, really efficient. And you also stop having to, like, you know, every time you open a file and you like see a random lemma in there, you're like, oh, is this ready or not? Does it depend on something above and not? You don't have to think about that. You do all of this here. The one issue with this list that I found over time is that it can get pretty long. So the thing that we did with Javier last week is to create this upstream dashboard, which puts together this idea of listing the files that can be upstreamed with extra automation to tell me which files I have already upstreamed, which files I have already opened a pull request for. So for every file, at least every file in the Mathlib folder, because that doesn't really make sense, it tells you which pull requests have been opened to that file without the link and complete dot at the start to the Mathlib report. And so this brings me two things. One, I can see that, oh yeah, look, this file I have already done it because this is my pull request. And the other thing it lets me is like notice in advance what possible conflicts with other pull requests that are going to like change things, how things work in a file or something like this. Here's an example. I don't know. I have one. Yeah, I have an example somewhere, but I can find it soon. Anyway, you like I spotted several pull requests like this, which were going to conflict with my stuff, and so I reviewed them so that it would get in before I opened mine or stuff like that. Okay, and once you have this setup, I think this is pretty good. There is another file another folder which I would like to explain, but I'm actually after talking with Kevin, I'm not so sure it's necessary. Because I was actually in my project, I am splitting things a bit more than that. If you open, this is my project. If you look at it, there's two important. Oh yeah, sorry, this is the wrong thing to show anymore, because okay, there was a Mathlib folder, but actually ran out of Mathlib stuff to upstream. So the other important folder was prereqs, which is like, you know, things which should be in Mathlib but are not in Mathlib yet. So typically the inner product, the LP norm, and all the things which I haven't told you about, convolution, for example, both sets. And after talking with Kevin Buzzard, it seems like we should probably just include those in the Mathlib folder, even though they don't actually correspond to a Mathlib file. I am not entirely convinced. It's kind of open to suggestions. The reason why I think they shouldn't is because they are much harder to PR. Like my, so I can show you. Okay, I will be done in like 2 minutes. If you look at the list of things in my repository here, this is the list of files that I can upstream, and you see I've kind of run out of things in the Mathlib folder to present. And now all of these are just very hard to upstream because of various different reasons. And they are not in the Mathlib folder, which kind of shows you, and it's up to discussion. And I think that's it. So thank you.
Okay. Do you have any questions?
Just a small one. You gave an example of a two-line lemma that's that had to be upstream to Mathlib.
Yeah.
You also talked a bit about whether there's many open pull requests and not many contributors, so maintainers that get merged them.
Yeah.
How long, on average, does putting a small PR that just adds a two-line?
So that's a very good point. I think the time it takes to get a pull request merged is inversely proportional to the exponential of the number of lines in that pull request. Maybe you cut off to infinity once it's like past 600 lines. It's definitely like it's definitely sublinear in the size in the length of the if you have like a two-line thing, it will be merged like very quickly. Actually, I have a screenshot demonstrating this because so there's maintainers, but there's mostly one maintainer called Johan, who does the bulk work of reviewing. So this is a picture of my notification inbox like a week ago or something. So this is Johan's avatar, and it's just like it goes through everything and merges it all, assuming it's like short enough and like uncontroversial enough. Right. So the usual reason you link it to something merged because there's like one bit that's kind of blocking your thing, and if you split that in two, then there's only the second half. Question?
I guess I have a question.
You have a question.
So could you go back to the slide where you had like the 1 plus 0 to the power of 8 and like the log?
Yes. So that was can you present, please? This one, you mean?
Yeah. Yeah.
Okay.
So you mentioned that the reason you need to write the 1 plus 0 to the power of 8 is because you need to bring it to the nice form where you can compare it with the thing over there.
With that, yeah, with that
yeah.
L8, yeah.
So I was wondering if maybe this can be done with like ordered rewriting, if like assuming a hypothetical ordered rewriting tactic.
So there's two sides to this. I mean, I'm really in favor of ordered rewriting in general as being a tool that's accessible. On one hand, I agree that it would be easily done with ordered rewriting. On the other hand, ordered rewriting might be able to like kind of let you be lazy in a way, which means that your proofs are not as nicely structured,
right? And
won't be easily modifiable later. Because typically, this 2 to the 156 has a change value maybe like 10 times over the course of the project. Because every time I see, oh, I can actually like gain a constant here, oh, I forgot a factor of 8 there, and so I bumped or like decreased that number by a small value every time. It's not very clear to me how you would do that with ordered rewriting, and also simply like just for presentation, how are you gonna like display a proof that shows ordered rewriting? So I think I really want to use cap proofs, but somehow I want to avoid those stupid ones. And I don't know how ordered rewriting would do that, but maybe it will. Questions online, maybe? Oh yeah, the use of finance. Oh, very good question, Eric. I handle the splits because I'm usually the one doing them. But this is actually this is currently a lot of manual labor. I mean, the way I notice it is like the import just fails, and then I like check one lemma which I knew was there and has change file in the Mathlib docs. So for people, I just go to like here and then I check, I don't know, something that moved recently, said.memo, and then I click on it, and it tells me, oh, now it's in algebra.group.pointwise.set.basic, and I rename the import to be that, and then I also have to rename the file, but it's kind of a pain because you have to like move the folder. I tend to agree that it would be nice to have something more automatable. I mean, hopefully, once I put something in the Mathlib, folder, it's not there to stay very long. It's usually like a few weeks at most, and this shouldn't happen very often. Yeah. But it's a bit of an issue, I think.
When do you suggest pushing to Mathlib compared to just having your own Lean Fourier projects?
So the way I work, but that's maybe just because I have too many projects at the same time. I basically just my base state is to upstream things, and when I run out of things to upstream, I go back to the core front and work with them. In practice, for people who are not that intense about upstreaming their things to Mathlib, I think like just spending like 3 hours once a week is plenty to make sure that everything is being looked after somewhat regularly.
Even if it's a project that's like not related to anything in Mathlib.
If it's a project that's not related to anything in Mathlib, then I mean, do you have things to put in Mathlib?
That's what I'm wondering.
Well, like I mean, I think it's very hard to have a project which does not add anything to Mathlib, because there's always like missing lemmas and stuff like that. I tend to agree that when you at least when you're used to it, it's kind of hard to see the value in like splitting off a lemma here and there and stuff like that. Because like typically if I show you my thing with my pull request with Javier again, this was he originally he hadn't written any of those lemmas himself. He like put them in lines into bigger theorems. And I was the one telling him, oh, you should split that off and you should make it a lemma. And once you make it a lemma, then you see, oh, it actually belongs to Mathlib. I mean, I'm not saying this is necessarily the case with you, because I know you're in computer science and things tend to be less reusable. But it's a question of training as well. Like you might actually be able to find things to implement.
Regarding the numerical balance that you had on log 2,
yeah,
the fact that you had to hard code them, I
Yeah.
read a few weeks back, Lawrence Paulson kind of showed an example in Isabelle Hall where he could just approximate them automatically via arithmetic.
Yeah.
Is there any plans to, for example, have some notion of computable numbers in Mathlib which would allow you to do such approximations with Mathlib?
Be the tactic you want to see. There have been people talking about it like regularly every few months. It has already a name. It should be called approx, which I think is the same name as Isabelle. Is that right, Angelique? You've never done like math that was dirty enough that you needed to call that tactic. Yeah, I don't know. I have amazing plans for it once it exists. I don't have personal plans to actually implement it.